Levi and John, what do you see on? Do you see screen sharing or not quite?
I only see me on one screen and then the camera looking at me at the other screen.
Okay. How about now?
Yep.
Yes.
Well, it's trying to load something.
Thank you. Well, many thanks for finding an opportunity to come. We may have some duplicate printing completed, but it means that someone can get twice as much comments.
I was late to reply you.
Huh?
I did not see the email early, so I did not able to reply you. I also printed this case.
Yeah, thank you. Well, it's better to have twice as much than twice as less. So we do continue to prepare to Sanibel meeting, and since we do have very large number of attendees, we split into sections, and today we go over those in black font, and next week we'll go with those presenters are in the red font, right? So that everyone will do the you are those, you do not need it. So we do have how many? Six presenters for 2 hours, which means that presentation plus discussion shouldn't go over 20 minutes. And please equip yourself with a pencil and do some comments. So even if they are not very friendly in form, whatever you write is very friendly in fact, because you help your colleague to improve material for presentation. So the first presenter will be Dr. Yulun Han, and I want to invite everyone to join me in congratulating him with, well, formally one may congratulate me with a little seed grant funded, but it was based on talent and writing skills of Dr. Han. So thank you.
Okay, so my topic is computational modeling of photopolymerization reactions of cyclohexane or CHS. So CHS has attracted much attention because it can be used as silicon sources to prepare silicon-containing materials using liquid-based methods. Also, this kind of molecule is a promising alternative to traditional monosilane in chemical vapor deposition techniques. So the preparation of silicon-containing materials from CHS follow a general chemistry. So basically, upon thermal treatment or photoexcitation, the CHS molecule will undergo ring opening polymerization to form polyethylene. And with additional thermal treatment, there will be some bond breaking events, such as the breaking of a silicon-silicon bond or silicon-hydrogen bond to form amorphous silicon. So this kind of chemistry has been studied by experimentalists, but the corresponding theoretical investigation is missing. So that's the reason we are interested in this process. And the method we use to simulate this process is time-dependent excited state molecular dynamics. Okay, So basically, here are my models. So we have two models, and in each model, we have two molecules. So in the first case, we have two molecules in a face-to-face configuration. Oh. Oh, it came back. Okay. So in the second case, we have two molecules in a side-by-side configuration. So what we did first is we run geometry optimization for these two models, and from here we can get the optimized geometry and some basic electronic structures. So here I computed the absorption spectrum. As we can see here, so both models show no absorption in the visible range. And here, this picture shows the liquid CHS. As we can see, it is also transparent. So this means our calculation is in qualitative agreement with the experiment. And next, we use this geometry optimized models to run TD-SMD calculations. And we have 3 trajectories. And in each trajectory, we have specific photo excitation wavelengths. So we have one excitation for the face-to-face model, and we have 2 trajectories or 2 excitations for the side-by-side model. So I'm only focusing on the first one. So here are my TD-SMD results. So as we can see, with the increase of time, we can see some chemical reactions. For example, at this specific time, it's 1626 femtoseconds. We can see the formation of a dimer. And at the later time, at 1980 femtoseconds, we can see 2 hydrogens are ejected. So here we have a dehydrogenated dimer. And one interesting observation is for this silicon, we have the coordination number is 4, so which is typical in amorphous silicon. And I guess here I need to back up a little bit. So basically in TD-SMD calculations, we have hard intermediates. So to facilitate the characterization of these intermediates and to remove structural ambiguity, we apply a post-processing technique. So basically, after the completion of TD-SMD trajectories, we extract the intermediates from the trajectory, and we run additional geometry optimization. This post-processing technique is independent of TD-SMD calculations, and it has no interference to TD-SMD. So after we post-process the intermediates, we can just characterize them. So here I show some examples. So this is the density of states for the cold intermediates. Interesting observation is the homolumo gap becomes smaller with the increase of time. So for example, here the gap is about 5 electron volts, but here we got maybe 2 electron volts. Here is 1.8. And another calculation we did is to calculate the emission spectrum. So here we use this equation to get the emission spectrum. So what we did is after we post-process the intermediates, we run additional adiabatic molecular dynamics calculations at 300 K. So here is the result. We can see with increase of time, we see a redshift, and in addition, we see a line width broadening. And finally, we can just get the calculated mass spectrum from TD-SMD trajectories. Here are results. So basically, the most obvious pick is the single monomer. And at this regime, we see some small fragments. This corresponding to the fragmentation. And at this regime, we see some large fragments. This indicates the polymerization process. Yes, the same.
Yeah, well, thank you. So, questions are very welcome. Any?
I have a question, Dr. Han. So you presented this 2 weeks ago, correct?
Yes.
Okay, what exactly have you changed from it since then, if anything?
I guess here, so basically my point is to show comparison with experiment data, just to justify our calculations. And another new data is the PL spectrum.
John has questions.
Yeah. So one question I have, so with the TDSMD results you show one of the trajectories for the face-to-face models, but up above you're showing 3 excitations with only one of the excitations being in the face-to-face model and 2 of them being the side-by-side. I'm wondering what you see in the dynamics for the side-by-side models and why you highlighted the face-to-face.
I guess one difference is the time at which the dimer is created. If I remember correctly, so for the side-by-side model, the dimer, the creation of dimer maybe happens at very late stage, maybe 1800 from the second. And also, in the face-to-face model, the fragmentation events are very reachable.
Okay, no, that makes sense. I was just curious because I hadn't heard you present this 2 weeks ago, so thank you.
More questions? I have. Well, it is a question maybe not for Sanibel theoretical audience, but for general chemical audience. You did mention the fundamental reaction steps, like ring opening, hydrogen extraction, and then you show that irradiation by light help to go through the steps. Although there are no illustrative evidence of this. Is there any information that help to see if through which mechanism it goes, or maybe some like energy of open the ring and then comparing to the energy of kinetic energy accumulated through the cycle? Some analysis on this side could be maybe appreciated by chemical chemists.
Makes sense.
Not actual question. I'm just wondering in the third figure of this mass spectrum.
This one?
Yeah, in the middle, is it 2 lines or just 1 line? It seems like there are 2 lines. In the middle, I mean the highest intensity one.
I guess there are 2 lines. So the other one corresponding to the monomer minus hydrogen. It's just one hydrogen atom ejected from the monomer.
So that means same number of neutral molecules and
Same number
with
of silicon.
Same number of silicon.
A different number of hydrogens.
Okay.
So what size of the system kind of feasible to calculate using this method? It's like you took over here like 2 cyclodex signs, or it's in a periodic box? I mean, so the system much larger? I have no idea.
So the question is how large we can go
How
for
large
this.
the system you can use to do this kind of calculations, like you know, to see the photopolymerization reaction?
I'm not sure about this the answer, but for this kind of calculations, it took several months.
Several months?
Yeah.
Ooh.
In the NERSC, it will be quicker, maybe several weeks. But still,
Yeah.
it's quite expensive.
Quite expensive, that's right.
So it is the reason why the actual experiment, if you see near on this panel, there is models, spectra, and then just a photograph of a beaker.
Mm-hmm.
So the actual substance is in liquid phase, so it's high density, they're stacked in a random, but out of this liquid phase only two are picked as a minimal amount to show the basic steps of reaction.
Just initial interaction between them and the bond formation.
Mm-hmm.
Okay.
More questions one, more questions two, more questions three, but thank you once again. So please return your written comments to the author so that he could work on further improvements. And the next presentation should be by around 40, if you don't mind to come and present. Do you recognize? It doesn't look like your.
For the most part, looks like a couple figures got changed.
It happens all the time in PowerPoint. If you do PDF, it stays in the right place.
Okay, so I think at least 3 of my figures got changed somehow when I emailed them, so you'll have to bear with me and use your imagination a little bit. So,
If it is critical, we can maybe do a.
yeah, because this is supposed to be density of states, this is supposed to be a different fluctuation, that's supposed to be density of states.
Okay, you can give general introduction, and I'll check if we can do better.
Okay, so
The PDF you sent with the meeting invite is what he was talking about.
I guess this one is like,
yeah, that's what it's supposed to look like. So you can follow along just on the paper. So.
Check if this one
yeah,
is.
this one.
No, it's good. So, my presentation, or what I've been researching over the last couple months is perovskite quantum dots. So, quantum dot, the reason that we're looking at perovskite quantum dots is because they're very good emitters. A lot of experimentalists have been able to get 100% quantum yields out of them, which is pretty good. But one of the issues that comes with these quantum dots is that over time they degrade because these are based on ligand passivations, and ligands have been, or the ligands for these models have shown to either, well, unbind from the surface, so it creates trap states, which over time reduces quantum yields, so they become unstable, basically. And then a popular method throughout the history of quantum dots is to try to get stable emission out of them, is you can dope them with metal or transition metal dopants, like manganese 2+, which is what we did for our models here. So there's an image of the perovskite quantum dot in the upper top left, where it's the outside is the passivating ligands of the carboxylic acid and amine ligand groups, and we chose those groups because that's what's experimentally.
Arnold, please do not be discombobulated or scared. I'm going to focus camera, and when I was doing it last time, things changed on the screen.
Oh, okay.
You are lucky. Nothing bad happens.
Nothing bad yet, anyway. So we chose these because those are functional groups that are used to synthesize the quantum dots, and we just use short chains because we just need them to be passivated correctly. And then these are the elements that make up the perovskite quantum dots, so cesium, lead, if there's a dopant, manganese, and then bromide. And so, yeah, those are the two models that we looked at for this system. And where am I going to go from there? So the size of the systems, the quantum dots are about 1.5 nanometers in size. So they're a little smaller than what's typically seen experimentally, but it's the smallest we can do feasibly for the computations that we were running. And so the methods that we use for the intrinsic quantum dot, we looked at just regular vast calculations, and then we also included spin orbit coupling calculations because with lead it has a heavy spin orbit coupling just to being a big metal ion. And then for the manganese dome models, we did spin polarized calculations because since we're dealing with transition metal, it can have various spin states, and we wanted to pick those apart. And then we also included spin orbit calculations with those as well for the ground state. And then we did molecular dynamics at 300 degrees Kelvin temperature attached to the thermostat. We did that for about 1,000 ionic steps. And then for the excited state dynamics, we used red field theory. And then to get the red field theory for the non-radiative relaxations, and for radiative relaxations, we use oscillator strings to get those. So moving on to the models that we looked at. So for this column is the intrinsic perovskite quantum dot. So here would just be a regular ground state without spin orbit coupling attached. It would basically look the same as if we looked at the spin orbit coupling dose, except the band gap would be wider because spin orbit coupling mostly affects the lead atom, which contributes to the valence band. So the lowest spin state will decrease the band gap just due to the splitting of the spin orbit coupling. So those were our ground state geometrized optimization for the quantum dots. And then we moved on to molecular dynamics. And then by using molecular dynamics, we can track the orbital energies through time as it goes on through the steps. And if you look at some of the peaks in the conduction band, you can see that there are states introduced inside the gap, which is usually a clear sign that there's a trap state occurring, or one of the ligands, or one or enough ligands come off of the perovskite quantum dot to introduce trap states. And then that's what this density states plot is showing here. I just picked one of the positions along the trajectory, did a single point calculation, and there's a faint little trap state near the valence band edge. And so that kind of shows that over time you can kind of get ligands coming off, going back on. If you run it long enough, you expect some ligands to eventually fly away from the quantum dot. So from molecular dynamics, we could go on to our excited state dynamics. So for non-radiative relaxation, we use red field theory, and these are red field tensors, which basically describe coupling between orbitals between states and the off diagonal. So if you zoomed in on the image, all the diagonals would be 0, and then states close to each other are going to have high bars, and then further away you get these decaying here. And then the very high peaks indicate that there's going to be a very high rate of non-radiative transition between orbitals. So we could see that usually it's actually the reverse. Or for typical systems, for like bulk systems, you would see that near the very high and low, or low in the valence band, high in the conduction band. Like these would be higher peaks, and as you get towards the band gap, there would be a slower relaxation. But here we see a kind of reverse trend, which is interesting. And that's probably just due to the confinement of the quantum dot, because the orbitals are squeezed together, so there's going to be higher overlap between them. So there's going to be higher non-radiative relaxation that goes with them. And then this is just a plot showing the non-radiative relaxation for a specific excitation. So we excited from HOMO -20 to LUMO +9 at time 0, and then over time it eventually decays, and we see for the intrinsic dot, the electron relaxes to the conduction band edge a little bit quicker than the hole relaxes to the valence band edge. And yeah, MATLAB didn't spit out numbers for me yet. I kind of have to work with the software a little bit, see if I can get tables of relaxation rates for a bunch of different transitions, but that'll be in the next edition of the poster. And then for radiative relaxations, we can see that so basically how radiative relaxations are computed is at each time step here, it computes an oscillator strength, which gives a probability of transition. So you can see that for earlier time steps, there's very small energy transitions occurring in the valence band and the conduction band, like in between those states, and that's what these. This is here just showing low energy emissions over time, and then eventually once they both relax to the band edge, we get a very strong emission peak coming from the HOMO-LUMO gap, which is indicated by these two plots there. And as expected, the intrinsic quantum dot shows a very high PL, or a very high intensity for the HOMO-LUMO transition, which corresponds to what you define experimentally a very bright light transition. So that's the intrinsic quantum dot with no doping, and then we move, and then now compare that to the transition doped perovskite quantum dot. So we found from manually setting different spin orientations, we found that this system likes the high spin configuration. So, so it's a spin 5/2 ground state, and so basically, spin 5/2 ground state, and we applied a spin polarized density states for this, and we find that the manganese dopants introduce two states within like what you normally think of the traditional band gap of the perovskite quantum dot. And then, so I'm just blanking on how the best way to go through this. So from the spin 5/2 ground state, there's 3 possible electronic transitions we can go through that we can have, which is kind of seen from our orbital diagram, which corresponds to our spin polarized calculations. So for the spin up transitions, we can have a metal to a ligand transition, so MLCT, which is shown in our density states there. And then we can also have a ligand to a metal charge transfer. And those can happen in the spin polarized cases because spin's a good quantum number and you can't have a spin flip in that basis set. But then there's also the possibility of a metal-metal transition. So we can have this spin up, flip up into a spin down. And for that we need to do spin orbit coupling because it can mix spin states and can gives you the opportunity for that transition to occur. And we characterize that in this density state, so we have a metal go into a metal there. And then we also characterize the probability that those are going to occur through oscillator strengths, which this plot was a little small. I did this today, so this one. So it's kind of hard to see, but basically what we see is for the metal-metal transitions, there's a very low probability of them occurring, around like 1.8 eV to 2 eV. So we have a small probability of metal-metal transitions. And then we also have, the red line is a small probability of metal to ligand charge transfer. And we also have a little bit higher probability of ligand to metal charge transfer. So basically, what we get out of this is that, well, the probability of optical excitations for 3 different transitions that can occur. So that's the ground state electronic structure of the doped system. So we'll move on to molecular dynamics of the system. And what we did is we tracked, same deal as with the intrinsic dot, we can track the how the energy states fluctuate in time along the molecular trajectory. And we can see that for the spin up cases, these the two topmost energy bands correspond to these two states here within the gap. And you can see that the states they don't change at all in time. There's no intermediate trap state that occurs in these systems, which is what you'd expect from a doped system, is to be unaffected by ligands popping off on the surface. So we see no trap states along our trajectory for the doped system. And then moving from molecular dynamics onto our excited state relaxation. So if you look at our Redfield tensors, you can see in the middle, those correspond to non-radiative transitions between the metals, the transition metal dopants. And then an odd thing comparing it with the intrinsic dot is it seems that putting the dopant in changes like the local environment. So you get a different relaxation rate like around the manganese dopant compared to if it was a lead in there. So that's just something we're still kind of looking through to try to explain why that is. And then here is just another excitation from HOMO minus 23 to LUMO plus 13. And in this system, it appears instead that the hole and the electron relax at about the same time, on the same order of magnitude of time anyway, to the gaps. And we see that in the excited state before it relaxes to the HOMO-LUMO, there's quite a bit of emission coming from as it relaxes to the gap. But once it gets to the gap, there's a very faint excitation corresponding to about 700 nanometers, which is a little bit lower than energy than what's experimentally reported for this transition dopants, but about in the right spot, but it's very low over time. And that's kind of the opposite of what we expected to begin with. We expected this peak to be higher over time, just due to the ligands or the traps being unaffected by the trap states. So I guess the conclusions from the study so far is that we have to rethink how we're going to or think of a new way to present the results. Because initially we were hoping to show that the dopant would increase quantum yields over time, but either there's something wrong with our methodology or with our intuition going into it about how this system behaves for emitting light. So I guess that's about all I have.
Okay, let's thank Aaron for detailed and interesting story. So, other questions?
No questions here.
Actually, I have one question. For me, it's interesting because as far as I understand, you work with, let's say, pristine structure of perovskite, right? But did you investigate any defects of this structure, how it can influence on properties of the system, and where you put actually these manganese ions? Where is the position of these ions? Because if you work with doping, let's say, you somehow need to put in good position these ions, right? To make this calculation accurate, let's say. So my main question is, did you try to investigate some defects in this structure?
So for your first question, John has actually investigated defects of just removing a lead vacancy. So he'd be able to explain to you better than I could the effects of that study. But for where I place the dopant, admittedly, it's kind of hard to see from the figure, but it's basically a 2 by 2 by 2 unit cell. And so really the only place to put it is directly right in the middle for it to not, because if you put it anywhere else, it would be on the surface. So in this case, it's directly right in the middle of the dot.
Okay.
So you can kind of think of it as like...
So you added these ions, you didn't exchange them with another, right, in the structure, as far as I understand.
Right, we put it into manganese and we remove the lead. So it's interstitial, or not interstitial, the opposite. Replacement.
Okay.
Replacement.
Hey, Aaron.
Yep.
Question about your format. When this shrinks down to 4 feet by 3 feet, first, is it the right dimensions? And secondly, are your figures going to be able to be recognizable? Because looking right now, they can be easily seen, but if they shrink by 4 times, they're going to be very, very, very small. Or how are you going to like counteract that?
Right, well this is a template from someone who's presented at Sanibel, I don't know, like maybe 3 or 4 years ago. So this format has been used before. I guess I can dig around in the office, see if there's posters in there to see how the figures turned out. But yeah, it's something I was thinking about. I guess I haven't gotten to the point of actually like looking at the max, like the biggest size possible for this format. But
okay.
So
just because
I have a comment to Levi. It is not restricted in vertical dimension. So the poster is mounted on about the height of human face, but you can make it longer up to the ground, and then invite visitors of your poster to lay down and watch the lower level.
okay.
Like John posted 2 posters last year, like that.
Levi, do you have questions as an expert in ligand to metal charge transfer states?
Not really.
Okay. John is lifting his hand.
Yeah, okay, so I have a couple of questions. So the first one, and maybe I just missed it, so when you're talking about this trap state, the intrinsic perovskite, did you see something structural that created this trap state, or is it just a weird shift in energy?
It's kind of hard to tell because I think it takes more than one, like pulling off one ligand to create the trap state, it seems like. I think there is maybe 2 or 3 ligands that kind of pulled away from the surface a little bit. And then once it relaxed, like, well, this peak went back up. So
it was almost like an under-coordinated surface atom?
Right, well, more like 3 under-coordinated.
Okay.
Because it seems like it was just more than one of them that was detached.
Okay.
Similar question.
John, would you permit you?
Go ahead. If you. Yeah, please.
So, what's the difference between the left fluctuation and the right fluctuation. It's just two different methods or different models.
Yeah, so this is the intrinsic. So yeah, it's just the intrinsic one. It doesn't need to be spin polarized.
Okay, so
And
if
then this
you,
one's for the spin polarized with the dopant.
okay, so if you just compare the spectrum, the right one is much more smooth than the left one, right? You do not have any spikes.
Right.
So why a single replacement can cause such huge difference?
Well, I guess.
Is
Well,
it
the thing is
single
that
run
it's hard. If you're talking about like states that are very close, very patched, it's kind of hard to see when one fluctuates to another.
Can I contribute
Yeah.
on the rights of co-author? So there are several unpaired states, and the density of states spin polarized in is unsymmetric. There are some alpha states, and there are no beta states at the same energy. Like there is something going up here and nothing going down. And these alpha states here contribute to the spectrum and some additional fluctuations. And in the beta electrons with spin down projections, just there is nothing in this energy region. Does that answer?
I guess you go just like these 5 states are going to be the 5 lowest states here, too. So, like, it's going to take a, like, I don't know. Well, maybe it's easier to see in this figure. So, the MN states are so within the gap that any fluctuations due to surface states aren't going to like interfere with these 2 states. Does that make sense? All right, back to John's question.
Okay. So I've got a couple more. So one of them is figures you have on top for the doped system. Oh, so the density of states for your doped system. So for the spin polarized, you show metal to ligand for the alpha and ligand to metal for beta. But as soon as you go to this spin orbit coupling calculation, you have metal to metal transitions. And so I'm curious which one you think is accurate.
Accurate as in
Metal.
you cut in and out a little bit.
Oh, so, well, in comparing the 2 density of states figures for the dope system, one shows metal to ligand and ligand to metal.
Yes.
And then the spin orbit coupling, you show metal to metal. Do you believe one is more correct than the other? Like within the actual experimental system, do you think it's metal to metal? Basically, do you trust the spin polarized or the spin orbit coupling more?
Well, just knowing the experimental results, because I probably forgot to say in the introduction, but experiment shows that the emission you get from these is about 600 nanometer, which is consistent with DD transitions.
Okay.
And if you look at just the band gaps for the ligand to metal and metal to ligand, it's like ligand to metal is like 3 eV, and then metal to ligand is like 2.4, so that would be more green. So,
Okay.
yeah, it's widely hypothesized it's DD transitions, so metal to metal.
Okay. And then, so my last question is based on the non-radiative and radiative for the dope system. So you're showing, one set of data. Is it for a spin alpha excitation? Is it for a spin beta excitation? Is it a combination of some sort when you're talking about these photoluminescence yields or the integrated emission?
So those are actually computed with spinor orbitals.
Okay.
So it's
then I would, okay. Well, yeah, I guess we were emailing back and forth about that. But then I would definitely clarify that that you're using the spinor orbitals in calculation of these type of rates instead of going two different systems, spin polarized fluctuations, and then just relaxation rates. Because I think that'll be interesting for people to see that it's actually spin overcoupling.
Mm-hmm. Yeah, I realize it's very ambiguous just looking at it. I'm just trying to not overwork myself of like putting in comments before I know how it's going to be formatted. So.
Yeah. Okay.
But it's a good idea. You're right to highlight that it's spin orbit coupling, because that's like.
Yeah, because I think it's much. Yeah, I think it's much more interesting to have that factored in. Oh, and then the last question I have, so with the single dopant in there, is it comparative to experimental dopant percentages that they use in quantum dots?
Yeah, as far as I know, because from what I know, it's experimentally kind of hard to figure out like the doping concentrations. But from just looking at synthesis, it's like mostly all the manganese that they put in, like only a small fraction of it actually enters the quantum dot, so it's very low concentration.
What is the order of magnitude? It's like 1 to 100 or 1 to million?
Maybe probably more like 1 to a million. Maybe 1 to 100. Well, usually if you have too high of a doping concentration, like the emission changes, it gets more red. Mm-hmm. So you can kind of infer it that way. So low doping will give 600. The higher doping will give more like 700.
Okay, so you're talking like, hundredths of a percent or something like that.
Yeah. I think here it's like it would be 1 to 500. About. I think that's about how many perovskite atoms are in it.
No.
Okay.
Or is it 300?
Should you count towards total number of atoms or number of lead ions that are replaced?
Oh, lead ions. So it would be like 1 in 27.
Then it would be like 4%.
Yeah.
Around 20.
Okay, so that's probably close to experimental then. Okay. Okay, that's all my questions for now. Thank you.
Okay, thank you, John. Are there more questions?
I had a question. What is that little small image right there? What did that represent?
Small image.
On the dope section in between the four panels?
Oh, that's my oscillator strengths. Or absorption.
It is a vision test.
Oh.
Yeah, it was something I just threw in last minute because I forgot to put them in. And yeah, they need to be in there somewhere. I just threw them in so I can mention them.
Austin, did you have any questions for just education? I have some very basic question. One to wording of the introduction. At the end of the first paragraph, you tell that manganese makes stable DD transition. What are experimental data? It is just stable or more intense?
Compared to what we have?
No. Purely in experiment. Does manganese make photoluminescence more intense, or it just adds stability?
Both. Well, it does do both.
So it is. It should be substantially intense. Intensity increase due to manganese.
Intensity of
photoluminescence or quantum U.
I don't know. That doesn't make sense to me because it still emits from the perovskite too.
Mm-hmm.
So it doesn't increase the emission from the perovskite. It kind of siphons emission from the perovskite into the dopant. And I guess I'm not sure what the energy transfer is, whether it's 100% or half.
No, observable emission intensity. not the internal processes.
I guess I don't know off the top of my head.
Okay, and a little provocative question, which you may get asked. What is the binding energy of the ligand or pair of ligands? And if it is substantially bigger than thermal energy, how can they desorb during thermal motion?
Well, just from the quick calculations I've done, it's shown to be a couple eV, which is a lot bigger than room temperature. But that kind of ignores the longer chains of these, because experiment there are like 18 chain carbons, and here we only have 2 carbons, so just the interaction is about a couple eV, but I would assume in reality the longer ligands would contribute to destabilizing, or entropic effects would decrease the binding energy.
And without an argument to experiment, you're computing binding of about 2 eV, and then you are observing molecular dynamics with ligand desorption. Are they in contradiction? Do not answer, just keep thinking, and it is standard question that people ask when trying to chew you. More questions to Aaron? If no, let's thank him. So what do we do? Probably Jared, did you send your...
Yeah.
Can you just resend now
So
to
how did you
different address?
Like for the drinks you want to geometry optimization, right? And then you just replaced.
So please, if you were making
So
comments,
that is the two additional.
please join me in returning them to the author.
Yeah, I should probably mention it.
Like, just look at the spectrum here and here. This is here you have also spikes.
And you have four more presentations.
My
Just
impression is
4 more?
this one
4
is
more,
like
yes.
geometry optimized.
It says
compared to
3
this
more.
one.
There is one late submission. That is going right now.
Do you think there is a major difference between these two?
Dimitri.kelly@gmail.com.
Yes.
Could
You
be
sent?
possible because, well, it wasn't me that actually optimized them, it was a collaborator, Dr. Interbed. So I know at one point this one was under optimized. I think that one would have been the same way.
No.
But I think, I mean, even if you look at these ones, though, they're still.
Yes. Can you please arrange distribution of your printed?
If you look at this one, but still, this one, unlooked one is all up is by the spikes.
Mm-hmm. I think they just have to be. Well, they have to be from the ligand. Like if you look at the oscillation of these, it's like it's very slow, so that would correspond to like a lead or manganese or something. Like if they're oscillating very fast, it's like a carbon hydrogen bond. So I'd assume that something like this looks like something from a ligand. Those all just kind of one trajectory, so I think it's just different ones kind of popping in and out.
So you are saying there are some bond breaking events.
Or not bond breaking, but it's just the energy of the system changes enough so it picks up different of those bonds. So that's why it looks so spiky. It's something to look at.
Jared, when you're ready, just attract our attention, let's see.
I'm ready. I'm just waiting to all of you ready. Yeah. So thank you guys. This is just one kind of introductions, and other part is from the actual last presentation. So I put few of my latest calculations and figures here. So layout is not final yet. I just put all of my stuff here, and then I will work on the decorations and other stuff later on. So first of all, as introductions, we know that the importance of the lead selenide materials, especially and they have in case of photovoltaic applications, they have some advantage for using the bulk lead selenide in other cases, but they have difficulties too. Then come up with quantum dots. Lead selenide quantum dots is also reported as a very efficient carrier multiplications and other applications. So problem is when we use the bulk quantum dots, although it has a very tiny band gap, but thank you. So bulk selenide has a very tiny band gap, like 0.26 to 0.3 electron volts. So that's advantageous to use in photovoltaic applications, but we need to control some factor like momentum conservations and other factor to create the multiple exciton or other kind of things. But in case of quantum dots, photo relaxation due to the phonon relaxation can be controlled, and also it increases the multiple carrier multiplications, but the band gap is very significantly high in compared to other one. Is higher than close to the 1 electron volt. So 2 nanoplates is kind of in between the two nanoplates and quantum dots and the bulk materials. So we hope that nanoplates can be more promising materials for these kind of applications. We can control all of these things. So I'm focusing on the lead selenide nanoplates by lead halide bridging. We consider this one because it's already we group from the Dr. team of groups also able to synthesize this kind of nanoplates in the control thickness, especially exactly 2 nanometer thickness. So that's how we adopt that system, and then we calculate this one for the excited state calculations. So in the first one, I take a look on the dose is the positive. First one is the total dose for the 2 nanoplates. It seems it's showing that symmetric dose like quantum dots. But if we want to do a positive dose for lead and selenides, in the conduction bands is mainly contribution from the lead, and in the balance band is mainly from the selenide. But in case of chlorine, because it's a bridging element, is important in this case. Chlorine is mainly contributing only on the conduction bands, and the contribution on the balance band is it's not concretely minimum, but they have less contributions compared to the balance band. So it's important to figure out how the whole can be relaxed on this one. In the next step, I take a look on the absorptions. There are different absorption spectra plotted here. In the first one, I just put this one is taken from the Dr. Klimo's paper. This experimental one. This is the absorption spectra around 1,000 nanometer to 1,200 nanometers absorption spectra absorption speed, and emission is around 1,000 is very tiny number, so it's not very hard to see here. And for this one, I just they have 2 absorption spectra. First one, black one, that one is as a 300 Kelvin absorption, and other one is taken at the 0 degree Kelvin temperature. So it seems that it doesn't change the overall feature of the absorption spectra, but at the higher temperature it's giving us a one very lowest energy peak, but it's not a very wide splitting between the main peak with that one peak. And another thing is, if you look on here, these materials, the band gap is around 1.25 electron volts, 2 nanometers band gap. And so on the main peak here, it's around like 2.5 times of band gap in here. So in the next step, for the relaxation process, we calculate relaxation by using the Tully fewest surface hopping methods. In this case, we consider I consider actually several initial excitation, but here we plotted only 2.5 gas because of we mainly focusing on the 2.5 gas times initial excitation by considering the absorption spectra. And other two absorption spectra, in this one is a time dependent, absorption spectra with the time is showing that with the time it don't change that much. It's almost very similar absorption, just only slightly change on the lowest energy peak one. And another one in the last absorption spectra, this one is actually now the real absorption spectra. This absorption spectra is plotted from the as all asymmetric transitions. If you look on this one, red curve is this one is plotted from the all transition which is asymmetric to the creating the hot electrons, and black one is all going from the which one is creating the hot hole. Hot hole means is the hole energy is higher than in electrons. So in this case, so importance of this one is showing that this main contribution is coming from the actually hot electrons. So and this one also averaged over 300 trajectory ensemble. So we can say that most of the transition could be create the hot electrons in the transition zone. And next one is the dynamics. For these three peaks, I was showing the dynamics with the three different initial conditions. And the first one I calculated from the initial by taking out all asymmetric transitions. I put the tolerance level as a 0.05 electron volts and take those all transitions and plot it with the relaxation time. And although it's showing that overall the wall line is not visible in the black and white print is not visible here. So it seems like almost all initially it's creating a more number of hot electrons rather than hot cold. So that's why the whole relaxation is almost is relaxing and is close to the bandage, but it's creating the hot electrons and is relaxing to the bandage by close to the 1 picosecond one. And in case of symmetric transition, when I put the conditions for the symmetric transition, relaxation rate is almost symmetric in the both cases with the time as initially in electrons and hole. And also another thing is I did not plot it here. We saw that when we calculate the all transition and we calculate this separate the symmetric and asymmetric in the both, it seems like that significant transition is coming from the asymmetric. So although it's showing the symmetric, but this is not that much important in our calculations. And then after this one and the next two plot is just showing the relaxation rate for electron and hole. As from here, it's also reported if you look on the first one, in the first figure, hole is relaxing almost fast, is very close to the bandage, but electrons is relaxing little bit slower than hole, but is very comparable in this case as one. And for the next two, and before going here, let me look in here. This one is I plotted because in our cases they have a chlorine atom. Chlorine atom is significantly lighter atoms in compared to the lead and selenium, but so it's important to look on the contribution of the chlorine in initial excitations. In the first two peak is this is the ensemble average of this all charge under your initial transitions, electron and hole. That means this one, electron and hole. It seems that the whole transition is mainly coming from this. I didn't put my system here. This one is actually plotted. This z-axis is the thickness of my system, and it's sum up according to the xy plane. So that means it's showing that this is the vacuum of my system, and this is my considered lead nanoplates. So most of the whole transition is coming from the in the core, right? So core means is like more from the lead and selenium, but in the whole is more comparable. The more contribution is coming comparatively from the whole to electrons. More contributions coming from the surface state. In the surface, there are chlorine atoms. Chlorine atom is a lighter atom, so it also affects the dephasing time. I will talk about dephasing later on. And this one is just a same plots for HOMO-LOMO. I'm just looking. If you look on here, the whole, HOMO band is mainly degenerated over the whole nanoplates, but in LOMO is mainly coming from the not the surface layer. The second layer from the surface is mainly contributions from here. So, and the next things I just look on the dephasing time, because dephasing time is important to predict a lot of different features like impact ionization and other things. But interesting result is our calculated dephasing time is showing that the dephasing time very, very fast. This is losing their coherent state almost instantly in the less than 1 nanometer, 10^2 time scale. To explain the reason of this first dephasing, we look on that because of surface state. In case of surface one, there are also chlorine atoms. Because of contribution of this chlorine atom, the dephasing time is much slower to compare the lead solid quantum dots or lead solid materials. And this also reflects the result can be explained from by looking on the FFT, fast Fourier transformations of this one. And from the experimental paper, in literature, if you look on this one in the quantum dots and lead solid quantum dots and bulk material, there are acoustic mode near 150 to 200, but it's in our system, it's creating the more acoustic mode in the higher than 200, and this mode can contribution to losing the coherency, and it's because of that this dephasing time is much faster. So for conclusion, this conclusion is actually a whole conclusion. I need to change this one. And one thing is important here is saying that the surface state is contributing significantly in our initial state. So initial and also because of this lead halide bridging element and lighter elements is changing the dephasing time significantly. And this shorter dephasing time could increase the possibility of the carrier multiplications like impact ionizations. And that could be one promising result. Another thing is we need to, and for the future calculations, we need to look on this because the experimental work, they also predicted that this could be synthesized by using the even lead bromide too. They didn't able to synthesize by lead iodide. We know that lead bromide is like heavier than chlorine, so we need to look on that how dephasing time and this one changing by using lead bromide synthesis. And another thing is from the dephasing results, this could be giving us a positive result for photovoltaic applications things. And that's all about my words for you.
Okay, but thank you, Jabbat. Any questions? We have forgotten since 2 weeks ago. What is dephasing?
So, in my calculation, I just calculate the dephasing between the two excitonic state, initial excitonic state with the relaxed state, HOMO-LOMO state. So, dephasing means how fast is losing their coherency between the two states. And do you want a more implicit result, explicit explanation, or?
I'm fine, but you're answering not me. You should reach.
Okay, because I need to actually more help with graphical and everything, but I don't have that right now.
More questions?
So maybe I have a stupid question, but somehow, as far as I understand, you work with surfaces, right?
Sorry?
You work with surfaces, yeah? Your work is about surface.
Yeah, I mean surface means a 2D nanopore, so surface is important.
Okay,
now.
so how many layers do you use in your system? It's like your...
Yeah, they have a 6 layer.
Okay, and
That's
how
why
many
actually when we
layers
calculate this one is
like
showing on the
relaxed
6
one?
layer. Right?
So you fix all layers? How many layers do you fix in your system? And if it's influenced somehow on properties, how you selected how many layers will be enough to...
Yeah, that is taken from the experimental work. The experimental, they are able to synthesize the control thickness at the 2 nanometers. So in the Relaxation 2 nanometer thickness, they have about 6 layers.
Okay.
Yeah.
More questions? On the top right, you do have rate of energy dissipation changes with time. Can you explain it for general audience? Why it should change with time? Typically, if it is a first order process, then rate should be constant, and you are showing that it increases, then decreases. So how to interpret and agree with it?
One is increasing, is like it should be in the coherence state at so it's following the Gaussian shape. That's why it's increasing, but and the later on is decreasing with exponentially. Is because it's following the same relaxation rate.
Can you have an intuitive explanation how this top right figures connect with your center bottom figures? Your blue relaxation, yes.
So in this case, in the one is excited from here to here, so it's creating an exciton here, and by these methods, this is giving us a coupling between the each individual in the consecutive state. So that's coupling give us informations, and we put the conditions here. This coupling is, if it's negative, negative means it's excited, so we put it as 0. So that's how we set up this our calculation in such a way that is going to lower excited state with the time. So that means from the higher excited state with the time is going down, and finally is going to the homologue. So exciton energy is losing with the time, and that can be, and the rate of this one should be exponential, is can be explaining from the using the coupling constant.
So by the time your excitation ends up onto lowest excitation, onto homoluma, nothing relaxes anymore, therefore rate of energy relaxation is 0. Therefore in your upper right, it asymptotically arrives to 0, right?
Yeah.
Okay. Okay. It
Thank you
helps.
for helping me out.
More questions to Javed? Anyone wants to please him by giving her time? If not, then thank Javed once again. And in the remaining 40 minutes, we have 3 presentations more. Braden is cordially invited to the stage.
Corrections.
I will distribute. I'll distribute. Just start giving general introduction. Right version?
Yes. Alright, so my work involves covalent functionalization of single wall carbon nanotubes. I won't be incorporating non-covalent, so I'll have to change the title. If someone wants to mark that for me. Our idea here is to take 2 adjacent ortho or 2 para positions along a ring and functionalize it with 2 defect groups, something like you can see here. you need two to fill the valency after breaking the delocalization around the ring. And we choose these we choose these defects here shown in this table as ones that we've explored. So you can see we have small defects, CH3 and an H, all the way to two long chains fluorinated, so C6 F13 chains, so they have a large dipole, and I'll come back to that later. So it's been shown that the orientation around the ring matters. So we define three directions relative to the tube axis, and I will call them L20, L80, and L-40. And we're working with the 10.5 tube, and incidentally, the L20 is very close to the 19.86 or something chiral angle of a 10.5 tube, and that's also kind of how we choose that. And shorthand notation for those is O+, O++, O-, and then for para positions, we have across the ring P+, P++, and P-. A little depiction here of an arrow group could be coming off of this, and across you have another arrow group in the para position going in the para minus, P- direction. Alright, so what we've done here, it's kind of blurry on the screen, but on the handout you can see some band gap comparisons. So this is a relative band gap, so I've taken the pristine tube, calculated with the minimal basis set SO3G. And on the first two panels on the band gap, I have shown three different basis sets that I've used per system. So one is where SO3G is for the entire tube and the entire defect. The second is SO3G is used for all carbon and hydrogen atoms, where the halogens, I don't think I have it depicted here, but I have mostly fluorines and some bromine groups. And so you can see that, and then all of them calculated with 631G star as well, and you can kind of see that comparison. It's interesting, because on one hand you have the, that's really hard to read. You have the SO3G on the top and the SO3G on the bottom, depending on the group that you're looking at. So the C2F5 versus the C6F13, it kind of flips directions, and we're not sure why yet. Running a couple more simulations with different lengths of chains, just to flush that out. And as you can see, then on the next four panels, we just have group comparisons for band gap. So some of them are blank because the simulations aren't quite finished yet. But most of them are roughly the same, depending on the group. But the major difference is the orientation around the ring. So the group effects are, on average, much less than KT, which on this scale is 0.25. But the orientation effects are much greater than KT, and so we can show that that is a somewhat tunable property of defect carbon nanotubes. And so also to kind of show that in the ground state regime is these molecular orbital plots. And I realize I can probably make that plot smaller because it's pretty easy to see, and put another one there as well. But you can see as I've arranged these O+, P-, O++, P++, O-, and P+ in degree of localization. So going from left to right, you have delocalized to localized in respect to the pristine tube, which I've shown on the very left. The only one that doesn't follow that is the C6F13. Again, we see some weird stuff going on there, where when you have the defect on the surface, it actually increases the band gap, which is something that we didn't expect at all. And we're just trying to make sure that that's not an error. but currently I've checked everything and I didn't seem to make an error, so I'm starting from scratch, running them over just to see if I get the same thing. But everything else seems to follow the same sort of trend. And then if you calculate the absorption spectra for each group, irrespective of the C6F13, they all follow the same exact trend. So you have the pristine at the top with its E11 band, and then you have, and so my colored ones, non-black, are the CH3H group, all calculated with STO3G. And it turns out all of the groups calculated with STO3G give the exact same trend with minimal deviation in the absorption energy and the smaller absorption band as well. Again, I've plotted the weird one out, the C6F13 kind of over top of this on the runs that I've done TDDFT for. And as you can see, it kind of pulls back from the pristine tube, which again is something we didn't expect, because it's always been shown that when you defect a tube, it will always shift it, or it'll always decrease the band gap. So we're looking more into that. So kind of what this says is that if you look at a basis set, if you're thinking about basis sets, changing the orientation around the ring, it doesn't matter. You can use any basis set you choose, and you'll get roughly the same trends. However, with different groups, obviously basis set is a little more important, especially when you have fluorines. And one thing we hypothesize about the fluorines is the increased dipole moment. And so we can take that as like an inductive effect, kind of pulling the electron density from the tube to the defect. And so we can look at that by looking at the natural transition orbitals, which I haven't plotted here, but I did on the last one, so I could add that here. But on the long chain fluorinated groups, we do see some of the wave function go up onto the defect, but not in the other ones with the less of a dipole. So that's the main story, I guess. There's a couple more small things, but that's the main idea.
Okay, let's then Braden. So who wants to please him by hard questions?
What is the STO3G?
It's a basis set for any methodology you choose. You require a basis set to. It's kind of like in PChem when we approximated electrons or ions as like Gaussian wave packets.
Yeah.
It's the same. Okay. Just the number of basis functions attributed to describing an electron.
Okay.
I have a provocative question. Carbon nanotubes can be fabricated with different diameter and chiralities, and this affects their band gap, which is important for applications.
And that's very well known.
Yes. Why should we, or whatever, why you or your experimental collaborators need to bother with defects if one can just fabricate right diameter? And so your top right figure shows how the defects adjust the transition energy. At least it looks this way. Can it be achieved just by changing the diameter and chirality? What is the benefit of defects? What are the applications where change of diameter will not work?
Well, there's a couple prongs to that answer, I guess. One is creating tubes is difficult in and of itself with just one chirality. And there's some, depending on the process used to make the tubes, of course, some chiralities are more prominent than others, so separating that is a big issue. So maybe one possible answer to that is if you are stuck with some tubes that don't give you the right transition energy, you can modify them at will with some extra chemistry afterward. Another may be changing the diameter of the tube doesn't give you as much of a range in the transition. I don't know the for sure answers of any of these that I'm saying, but
and do you know the applications for this defects you would like to help?
Probably in more in emission settings, like a telecommunications aspect, maybe.
Why? Why telecommunications need emission at infrared range?
Kind of like, or you can think of it as like a, I don't know what word I'm looking for.
Less losses in fiber optics? I don't know. I'm just curious.
Maybe.
Key fobs.
Yeah, that's what I was thinking of. Like a tube, like a sensor. So you press that. You know, some calculators have that too. You know, they used to ban graphing calculators in high school because you could use infrared communications between calculators.
In the absorption panel, the second and fifth panel, there are two absorptions for two basis N, right?
Yep.
So in the second panel, is showing that is expected is blue shifted by changing the 631G star. But what happened in the fifth one, the EU11 transition is almost exactly in the same energy level?
Mm-hmm.
So what's the reason that?
Yeah, so I kind of glossed over that because I don't know the answer yet to for this question. But if I calculate the C6F13 with like the 631G star on the fluorines here, in that position only, you get the opposite trend of everything else. But if you look here and you calculate with STO3G on all the atoms, you have the exact same trend. I don't know. I'm running a lot more simulations to try and figure out the answer to that, whether it's my mistake or something else at play. But
it's very unusual to give exactly same absorption spectra by using 631G star, isn't it? Isn't it very unusual to produce exactly same absorption spectra by using 631G star and STG, STU0? But they have a fluorine in there, right? In your calculations?
yeah, in the black curves that have overlapped with the, yes.
More questions? John has something.
So in looking at these defects, you list multiple types of defects. Are they standalone or do they come in pairs? What type of effect are they if they're matched, if they're not matched? And kind of the end result.
Yeah, I haven't done any ones where I have two large groups competing. It's usually either the same group on the ring or one group and a hydrogen. So I don't know if I've shown, I don't think I've shown any plots on that. Well,
do you have an initial guess of what might happen?
Well, we're kind of hypothesizing, the inductive effects of the dipole moment of the group would change, and the sterics of the group too. So it's, if they're, say, the long chain fluorinated groups, you're going to get some Coulomb repulsion on the group, so they'll be pushed away, coming closer to the tube, and so we think that might have an effect as well. But we just haven't run enough simulations on those types of things to really get that idea. But the smaller groups, we don't see that much effect between if you have two groups or a group and a hydrogen. So,
in continuation of John's question, can you do just one group without hydrogen? Why don't you do it?
Well, you break the valency of the ring. You have a charge center.
So you're telling it will be very energetic when favorable?
Yeah,
Or it will
it'd be a very
unpaired?
reactive site, I guess, but
So it will be a reactive site with unpaired electrons. And it will catch second group naturally on experiment.
yeah.
Okay. And it is therefore you do this nomenclature of ortho and para things.
Yes.
It is how two groups relate to each other. Because if there is only one group, there is no reason. It's like Alice in Wonderland side of the mushroom. More questions to Braden? If not, well, thank you once again. And we have two talks in 25 minutes. Alice is invited to tell the story.
It's hard to read off the screen. Okay, so my research is on cadmium sulfide quantum dots, which is kind of similar to obviously cadmium selenide, which is research that was done previously, but I've only ever worked on cadmium sulfide, so I don't know anything about cadmium selenide. But previous research was done in propylene, which is a non-polar solvent, on the effects of thiol on the surface when it converts to thiolate. So thiol, when it's on the surface of a cadmium sulfide quantum dot, is very optically active and produces it absorbs a lot of light. So it's more favorable than thiolate, which turns out doesn't really have any good optical properties, and is often, so the thiol is often deprotonated into thiolate with the proton going to the surface of the cadmium sulfide quantum dot. So we chose thiol because in comparison to carboxylic groups, it has a better optical yield, but carboxylic does not favor well in any sort of polar solvents. So we're trying to find a group that will allow this quantum dot to have an optically active surface and be in polar solvents, like possibly water. But the polar solvent used in this experiment is acetonitrile. So my structure here, which is kind of small on here, but I hope on a poster it'll be bigger. I don't really know. Anyways, so we've got 4 layers, and in most of this data, it's observing just one thiol or thiolate on the surface, rather than a whole bunch. And then there are 2 different options for each of these choices. There's one that's fully passivated with amine, so it'll be 20 amines on the outside of it, which I don't know if you'll be able to see that. Should I, in the bottom corner, this part? Can you see that? Would that blow up on the poster? I just need help, that's all. Yeah? Okay, I don't know.
You can do an experiment, but there is no guarantee that it goes.
Oh no, not on this, but like on a poster, would you be able to read it?
Probably.
Probably? Okay, I mean, yeah, it doesn't
But
really matter.
you can come, Alyssa, if you want to expand it to explain, you can just comment.
Okay, alright. So there are 2 different main points. There's ones that are passivated with 20 amines, and then there's ones that are passivated with just a single thiol, and there's also another fully passivated with the thiol or thiolate. But basically in the bottom, the F category right at the bottom here, is showing the difference between thiol and thiolate. And in the charge distribution, you can see over here that this is more electronegative, so it tends to pull the hydrogen or the proton from here to the surface, resulting in a thiolate, which we don't want. So our goal was to figure out whether or not we could kind of stop this process from occurring. So the first research is done in a non-polar solvent, which is propylamine.
And this is the binding energy of the ligand to the surface of the quantum dot. You can see that the thiol, depending on whether or not is that has a large binding difference, whether or not it is passivated by amine or without amine. Because this line, the solid line right here, is passivated fully with amine inside the polar solvent, which pretty much blocks the effect of the polar solvent and continues the trend, which this point is the same as this one here. But the one on the left just goes up, and the one on the right goes higher. Anyways, so without amine, the binding energy is practically, the ligand is practically completely withdrawn from the quantum dot because of the polar solvent, which is not optimal, I guess. And then we have the thiolate, which does not have a proton, meaning that the proton could have gone into this, like the solution, or it's just not there. And then the blue is the thiolate with the proton on the bottom, as shown in the bottom left-hand corner. But basically, it's the same situation as far as the amine blocks the solvent and then keeps a steady around 1 for the binding energy of EV. For the thiolate without the proton, but without the amine, the binding energy goes up, which means that it's not attached to the surface and is pulled out by the solvent. And then the proton, just by itself on the surface, stays relatively the same whether or not there's amine or not amine, and it doesn't matter with the solvent. So that's staying pretty constant, and so is the thiolate plus the proton. And then below, I have, so dash lines. I know you can't really see it, which is a bummer. But so dash lines, which is going to be this one right here, have no amine, but they do have one thiol or thiolate, depending on the symbol of the, depending on the color of the line. And then solid lines, this one right here, has the amine, it's fully passivated by amine. And then the empty symbols are acetonitrile, and the propylamine symbols are fully filled symbols. So I know that's a lot of information for one graph, but basically what you can see here is that in acetonitrile, the bond distance is increased pretty significantly. I don't really know what's happening there, but I'm gonna figure it out. I don't. Yeah. Anyways, so it's consistently being okay. I'm sorry. I need to organize my thoughts. Okay. Yeah, the acetonitrile. These two lines right here are consistently higher than the thiol with propylamine, which means that they're less bound to the surface, resulting in the thiolate being pulled away into the solvent. And this is my most important data down here, and don't worry, I have more, I just haven't been able to put it on there yet. So it's hard to see, and I think I'm going to change this, but the dotted lines here are the ones done with amine and without amine, and then, okay, well this is done in propylamine. Sorry, I did not put that on there. But basically what this is showing, well, the solid lines are propylamine, the dotted lines are acetonitrile. Yeah, shoot, no, I messed up, sorry. Scratch all that. Okay, this is done completely in propylamine. The dashed is with no amines, and then the solid is with amine. I had it right in the first time, and then I need to put, obviously, the solvent on there, or else I'm going to forget. But basically, you can see, this is supposed to be the dotted line. You can't really see it on here. I thought you would be able to, but you can't. But it's right next to the line for the quantum dot, which means that if there was more than one thiol or thiolate on the surface, this is thiolate, so if there's more than one thiolate, or potentially 20 thiolates on the surface, it could create a trap state, which would make it so that there would be no optical properties to it, or no absorption, and so then there would be no emission. Basically, it's showing that without a mean, there will be trap states, but there's a possibility that with a mean surrounding it in propylamine, that there might not be a trap state. And then this is all in acetonitrile, and dashes with no mean, and solids with a mean. And this is the data that we were looking for, is because both of these are relatively far from the quantum dot line. So that means that the possibility of them creating a trap state when there's more than one of them is less likely, just because it is moved back from this, like, from the potential, like, because it goes from the quantum dot here to the quantum dot here, so it's less likely to move in front of that and create a trap state. And then, yeah, I don't know, I know what this is, but I don't know what solvent it is. So I'm gonna skip that for now. And I'll have better writing on it later. But basically, acetonitrile does pull the thiolate or thiol more into the solvent, but does result in a more stable optical emission. So it's kind of a give and take whether or not it will be more useful in the end for optical properties. So, yeah.
Okay, let's thank Elisa. So, other questions?
So it's still unknown what these in the bond distances peak the jump in energy. Still kind of have an idea.
For this part right here?
Yeah, that's point, the highest one.
I think it's because that the polar solvent is pulling the molecule into, not the molecule, the ligand into the solvent, rather than having it, like, the attachment to the surface isn't enough to keep it there. So, I mean, I'm not 100% sure. I have more data as far as I have the bonds between the sulfur and the hydrogen, whether it's the surface or the ligand to the. I have more. I haven't been able to get it done. So.
Yeah, probably you anyway need to recalculate that point, so it can be different energy. There's something wrong probably happens.
More questions?
Kind of simple question. With which software do you use to plot this partial density of states?
I use, well, I did it in, okay, software. Sorry,
Okay.
a second. No, I know what the answer is, I just can't think.
She used the Gaussian to take the
Oh, that was the answer.
and then
Okay.
plotted it. The movement is great.
Okay.
Sorry.
More questions? What at the end you were telling about trap states. So what are trap states?
It's when so this is the Hodo, and this is the no, this is the Ludo, this is the Hodo. So basically it's when it goes from one area of the quantum dot, which could be the ligand, could be this, but for all of the cases, the Ludo is the quantum dot, which is like the density of states is on the quantum dot. And then when it goes to the ligand from like the lowest unoccupied to the highest occupied, if it goes to the ligand instead of the quantum dot, it creates a trap state, which means that there's levels inside of like
undesired localization.
What?
Undesired localization of
Yes.
electron.
Yeah. Exactly.
Okay. More questions to Alisa? If no, let's thank her once again. And we do have last but not least, Landon Johnson, and he's debuting, making it for the first time.
Yeah.
Because the rest of us did practice it.
So I have a very rough template of my poster at the moment.
Oh, you weren't the only one.
What's that?
You weren't the only one.
Yeah.
So please do not hesitate to Right, rude comments.
Yeah. Yes, please
Or
let me
maybe
know
rest
anything that, if any of this is not clear at all, let me know why or what would help make it more clear. So what I did is I took some MATLAB code that was designed to model electron dynamics in a given potential, and I input ab initio data collected from Aaron, and I used that to figure out what the probability of transmission of an electron from the dye to the perovskite would be in a lead halide perovskite solar cell. So what I altered in each run was the initial momentum of the electron. So, I guess what am I trying to say with this? I tested two different configurations of the solar cell. There's one that is through space where I suppose I should mention that the dye is spiro-omitad. I don't know if that's how you pronounce that at all. I'm not a chemist, I guess. So there's a through space model where the spiro-omitad and the perovskite are just sandwiched together, and then there's a through bond model where the spiro-omitad has a methoxy linker group to actually create a chemical bond to the perovskite. And what that results in is a difference in the potential barrier. You end up getting a small well right here, and it reduces the width of that barrier. So I guess what I ended up finding is that the probability at most, what am I trying to say? In the slightly ultraviolet to visible range, there's a significant advantage to using the through bond. Once you get up to extremely high wavelengths, there's not really too much of a difference, but you're probably not going to be getting too much of that from the sun anyway. I haven't rehearsed this at all, I guess, so I'm just kind of winging it right now. So I suppose the way that I got these graphs was to set basically a cutoff right at the peak of this well here, and I guess the density of the electron that's still on this side compared to this side would give me the probability of transmission of that electron at whatever given initial momentum. I should also mention that I use that momentum to calculate what the wavelength would be of a photon that excited the electron. Yeah, there's not really too much to it at the moment. I still have to do some more data because I just had to recently rewrite the code to make it more appropriate. Because the code has periodic boundary conditions, so what I did is I basically extended the boundaries out to a far enough point that none of the electron density will actually be able to get across and interfere with my data like I had in physical chemistry last semester. Yeah, so it's pretty basic. This is what I have at the moment.
Okay, let's thank London. Any questions are very welcome.
Yeah.
It's not exactly research-related question. So what is the importance of starting these two processes through space and through the bond?
There are different ways that you could make the solar cell, I guess. This one would be a bit more cumbersome to actually do, but it would end up yielding a more efficient solar cell in the end. I guess I haven't run it since I've rewritten the code, but I also did, oh, I never mentioned that. Okay, so normally when light will shine on the perovskite, this will be the optical absorber. And what will happen is a hole will actually transfer over to here. But with the code and the potential file that I have, this is all based on the electron. So I'm treating it as equivalent to move an electron from the dye to the perovskite. So, let's see. I completely forgot what I was trying to answer. Oh yeah, the importance of through bond versus through space. So when I ran this last time around with basically periodic boundary conditions right at the edges here, I didn't see any significant difference when starting the electron from the perovskite and sending it to the dye between either of the configurations, but sending it in the forward orientation, I do see at least a notable difference here. And I suppose I did a log plot here because it's kind of hard to see if you do just a standard, not logarithmic scaling there. Does that answer your question at all?
Yep. More questions or suggestions? John does.
So you mentioned a little bit about localization of where the hole and the electron are, and you're discussing electron population in terms of these green and red figures, or green and red lines in your graphs. So are there specific potentials that you used in modeling the wave transfer from one potential to another that correspond to energy levels within the perovskite and the dye themselves? And if so, it might be helpful to show a little bit of that maybe in your methods to give a more of a physical picture of the methods themselves.
I guess, are you asking if I used like eigenstates of the potentials in those areas, or?
Sure. Yeah, I guess that's one way you could interpret it. Or did you just select like the energy gap as a potential barrier that you needed to cross?
So I suppose what I did is I modeled the electron through a Gaussian wave packet and just gave it some initial momentum towards the barrier. And then I guess I also never mentioned, this is the beginning of the simulation. This is when it first makes contact with that potential barrier, and this is at the end of the simulation. Yeah, I probably should have said that. So I'm just starting it as a Gaussian wave packet, and then sending it at this potential barrier and watching what happens, essentially.
Okay, so is the green figure taken from a lockpot file then? That's like the potential for the system? Okay.
Yes. I should also have mentioned that.
John has more questions.
So I guess I have one more question. So your top two figures on the right, and then your Excel plot that you have. So you're showing these transmission probabilities for an extremely high wavelength, where, I mean, to me, if you look at your Excel plot, like the transmission probabilities look to be fairly similar. So obviously one is with time and one is, the x-axis is photon wavelength. So there's obviously some kind of a decay about transmission probability. Is that the importance of plotting it against time versus just what the transmission probability is at a specific wavelength? Or how is the probability calculated for your Excel plot compared to what you show in your top two plots?
So what I did is I basically used this this percentage right here, because this is telling me how much of the electron is actually across the barrier here. So once it plateaus out, I use that value. And I could probably change that too. I was in a hurry, so I tried to do what I could.
Okay. And then did you calculate any type of rates, like rate of transmission, or however long it took to get to that plateau state? Do you think that might be something of value?
That was what I did last semester, so I could certainly do that again.
Okay.
Because that would just basically, I guess as far as I understand, I could interpret that from the slope of that line there. But yeah, that wouldn't be too difficult. I would just need to actually sit down and do it, which I'm planning on fleshing this out a little more this weekend, so I could definitely include that.
More questions?
Yeah. I guess I have a question, and just from visualizing your Excel graph that you have there, it looks like your through bond model is consistently decreasing, or it doesn't in comparison to the through space model, it looks like there's almost a little hump that it comes back over again.
Oh,
If
you're
you see
talking
what I'm
about,
talking about?
yeah, this area down
Right,
here.
so like why does that happen as far as your understanding?
I am not entirely sure why that's happening at the moment.
And I guess another question too is like why isn't that being experienced in the through bond model?
I don't have a good answer for that at the moment.
I wouldn't either, but I'm just curious to why that's happening.
It might have something to do with where I'm placing the divide. So basically how this ends up getting, well, no, because those points are all at the end. I did notice that when I was collecting the data that at some of the lower momentums, I actually, I would get a higher transmission probability in the through bond model, and then it would drop back down. Yeah, I really don't know how to explain what's going on there. That might just be a limitation of my method of simulating this, I suppose.
London? Oh.
Yeah.
So that kind of brings me, how do you know this is accurate, or are you comparing with anything other than just the potentials that were given?
I have not run any sort of verification at the moment, no.
Did you saw data from the literature on the similar systems? How do they compare with what you found?
I would have to look at that again and do the comparison.
What is tunneling?
That would be when there is a higher potential barrier than the electron has. The potential barrier has a higher energy than the electron does, but there is a non-zero probability that the electron will be found across that barrier, even though it started on the one
How
side.
does this concept relate to your images and calculations? Where is this potential energy higher than electron energy?
That would be right at this barrier here. So I suppose I should also mention that the energy on here is not to scale. This is kind of more of a, it's scaled to be something that you can look at visually. So this energy is actually much, much smaller than this in most cases.
You're telling just scaling
the electron energy as opposed to
energy or just probability?
Oh, yeah, actually, yes, that is just probability on the, yeah.
Is that probability of it?
Yes, the red line would represent the probability of finding the electron at that location.
And at the same time, it is offset by the energy.
Yes.
Okay. And John immediately got enthusiastic and wanted to ask something more.
Well, so what is the potential energy barrier here?
Oh, you're talking about the height of it?
Well, yeah. So put it in terms of electron volts or nanometers. Equivalent to whatever initial momentum you're giving the wave packet.
Yeah. If I remember correctly, this is in atomic units, and the potential, just the potential, should be to scale. So I guess it looks like somewhere between 2.5 and 3 atomic units of energy, which I would have to think about that conversion.
Can you just point out the barrier height for this
Yes.
potential? Where is the barrier height?
I should probably label.
London, I'm a little impatient to show it from there. If you point on this energy change,
Yeah.
you have a huge energy,
Right.
like 40 electron volts.
Okay.
No, the barrier is like from
50.
from here to there, and it will be maybe 3 electron volts.
Oh, yeah.
Much smaller.
Yeah.
Just to overcome this barrier.
Right.
So
yes.
being on a die and transferring to a semiconductor. So it is not too much.
Mhm.
More questions to London? More questions 1? More questions 2? More questions 3? Thank you once again. And please submit the written comments to authors. The larger amount of comment, the better is for the author. So many thanks for investing your time and participating in the discussion. Meeting is dismissed. Next time, those who are typed with red font will present for the second time. Right? 2-week period. If you present it today, you'll relax next time.
Get one more, right?
Done.